Okay, so we're doing the last example now. The Maclaurin series for e to the x is given, as well as the general term. The continuous function is defined by this crazy equation right here, f, and we're told that f of 1 is 1. The function has derivatives of all orders at x equals 1. It says write the first four non-zero terms in the general term of the Taylor series for just e to the x minus 1 squared. So up here, anywhere where there is an x, we will replace it by x minus 1 squared. So part A is e to the x minus 1, oops, I don't know why I wrote that there, squared is equal to 1 plus x minus 1 squared plus x minus 1 squared over 2 to the 4, actually, sorry, plus, that's a 4, plus x minus 1 to the 6 over 6, plus general term, this would be x minus 1 to the 2n all over n factorial. Okay, so let's move on. B, use the Taylor series found in A to write the first non-zero terms in the general term of f. So this is our f right here. So here we go. So f of x is going to equal, I'm going to take the first few terms. I'm going to take 1 plus x minus 1 squared plus x minus 1 to the 4th over 2 plus x minus 1 to the 6 over 6 plus x minus 1, 8 all over 8, and then we're going to say minus 1 all over x minus 1 squared. So if we simplify this, we get 1 plus x minus 1 squared all over 2 plus x minus 4, I'm sorry, x minus 1 to the 4th all over 6 plus x minus 1 to the 6th all over 24 plus x minus 1 to the 2n all over n plus 1, and that's a factorial. Okay, so that's part B, and part C is going to ask us to use the ratio test to find the interval of convergence. So the limit as n goes to infinity, and we're going to go ahead and go right to the flip the guy stage. So this is going to be x minus 1 to the 2n plus 2 all over n plus 2 factorial times n plus 1 factorial all over x minus 1 to the 2n equals. Okay, so we're going to do a bunch of multitasking here. I know these will simplify. Bring that out front. X minus 1 squared goes out front, and then we have the limit of n plus 1 factorial all over n plus 2 factorial. Now remember, n plus 2 factorial is equal to n plus 2 times n plus 1 times n, and so on. And this part right here is n plus 1 factorial. So n plus 2 factorial is n plus 2 times n plus 1 factorial. Why does that matter? because that's going right there. So the n plus 1 factorial and the n plus 1 factorial will cancel. So what am I left with? X minus 1 squared, the limit of 1 over n plus 2. Well, what does this limit equal when n goes to infinity? This is going to be 0. So we're going to have the absolute value of x minus 1 squared less than 1. As you can see, this is always 0 because we're multiplying by 0. Therefore, that means it doesn't matter what x value I put in there. Since I'm multiplying by 0, this was always going to be 0, which is less than 1. Therefore, our interval of convergence is going to be from minus infinity to infinity, or written this way. And this time we don't have to check our endpoints. Looks like my paper moved around quite a bit. Now for part D, use the Taylor series for f about x equals 1 to determine where the graph has a point of inflection. Point of inflection is a second derivative question. And remember, you have a point of inflection when you have a change on the second derivative changes either from positive to negative or from negative to positive. So we know that we have f of x, so we need to calculate f prime of x. F prime of x is going to be two times x minus 1 over 2 plus 4 times x minus 1 cubed over 6, which when we simplify will be x minus 1 plus 2x minus 1 cubed over 3. When I evaluate, when I evaluate the first derivative at 0, I get 0, which is fine. I don't really care so much about that. Now I'm looking for the second derivative. The second derivative is going to equal 1 plus... Okay, can you stop? Shut the door. Don't let anybody in. Seriously. Go out. Just go out and stay in the hall. I need 1 minute to finish. X minus 1. So